All right, let's go ahead and talk through some of the information necessary to complete the math sort of questions on test 3. So from folder 3A, question 1, just the very beginning of the module, we have a question talking about the density of a rectangular prism, a boxy block sort of shape. The formula for density is mass divided by volume. So textbook uses rho, it's a Greek letter that often stands for density. Sometimes we'll see density as a capital D, but it is meant to be the same thing. Now, if you think about what the shape is, it says rectangular, so we think rectangular prism, or again, like a boxy sort of shape, then that's going to mean for us that volume is equal to length times width times height. And if we know how to find volume and we see where volume is in some other formula, then we can take the stuff that it's equal to and replace it. So if we make that substitution, then rho is equal to mass divided by length times width times height. Okay, then this one's an interesting question because you can actually change several different things or different combinations of things and still get independent, unique answers. So let's do the easy one first. If we take the mass and we adjust it by some factor, so for this review, I'm going to use 0.5, just like I did on the other ones. But if I take my old mass and I multiply it by 0.5 and use that to work a new version of the question. So again, we could use this one. We could take 8.51, multiply by half, do all this again, and then see how the answers compare. But I prefer to use just sort of the brute force algebra or logic to see where this is going to go. So ratio of the new mass to the old mass, we get 0.5. And then if none of the measurements have changed, then technically on the bottom, we have 1 times 1 times 1. So that's just going to give us the factor back again. Now, what's interesting for this one is that you might be told that one of the perpendicular measurements has changed, or two of them have changed, or all three of them have changed. You have a lot of options for how this could be set up, and you've got to pay careful attention to what that's going to mean. So think about that. This could go a few different ways. You could end up with, you know, the mass in this case wouldn't be changed, so you'd have 1 on top for the mass. And then depending on how many of these changed, you would see that factor if only one of these changed once, or you could see it twice. And it wouldn't really matter, how you labeled these or what order you put them in. Or you could see it for all three. Keep in mind what that means, and that the ones in these aren't going to change the value except that they're holding technically the factors down to the bottom. But this one is going to be basically 1 over the factor, so the reciprocal to the factor, which in my case makes 2. However, if 2 of these different measurements have changed, what we end up with is 1 over the factor squared. Okay, and so that's 1 over 1/4 for me, and that's going to end up making, once it does the reciprocal and flips back, it's going to make 4. So the reciprocal of the factor squared. Or if all three of these have changed, then technically what we have is this thing raised to the third power. So a half raised to the third power is 1/8, but that's really 1 over 1/8. And so it flips back around and becomes 8. So there are actually several versions of this question and different ways that this could be asked. So just pay attention to that. Make sure you read carefully to see, out of the 3 measurements, how many are being affected, because it will make a big difference. Okay, so looking at the next one, we have an object that is under a fluid and is experiencing pressure because it is under a fluid. Very simple formula, still in section 3A or week 3A with our notes. If we look at question 4, because this isn't physical contact pressure, we can't see how a water molecule pushes on another water molecule and so on. Then we look at how they're packed into a certain amount of space. And that wording is very important because we already have a definition that talks about mass and space, right? Mass divided by volume was density here. Then, because it requires force as part of the definition, technically our original version of this was force divided by area, then gravity has to go in. You want to keep in mind that density had mass in it, and then so then mass times gravity makes force, and that's kind of how the rest of it works out. If you're a little bit creative, then you can think about what density means, and you can force this to come back around and still be force over area. But for right now, it looks considerably different. Okay, but that's actually all we need to get started with this one. The height is the height of the column of water above a certain point, which really ends up being kind of like depth. So I guess it's a matter of perspective there. But if the depth underwater, or again height with the way that these pictures are usually drawn, if that's adjusted by some factor, then I hope you'll notice that nothing really fancy is going on here. So we would end up with 0.5 for the ratio of the heights or the depths between the different versions of the questions, but the density would be the same, the gravity would be the same, and that's just going to give us the factor back. Okay, and then if we move on through the row, I think you can probably see what these are going to do, but let's say that the density's changed. So in this case, maybe it's not water. Maybe it's adjusted by a factor of 0.8 and is something like alcohol. Now, I don't know where you would find several meters deep of ethanol or something. I don't want to know. That sounds scary. But whatever, mathematically, we can work it out. It's not an issue. And so if we have that adjusted by some factor, then the depth or the height of the column of water is not changing, but the ratio of the densities would be 0.5, right? This one stacked over that one's going to cancel and give the decimal back. Then if we assume Earth gravity in both cases, then technically we'd have 9.8 over 9.8, ratio of 1, and so this is going to give the factor back. Okay, and then the last option, this would be a bit strange because we tend to work on examples that are on Earth because, we spend most of our time on Earth. But technically, we could work a similar question. This might make more sense for having the weird densities because maybe we're on, I don't know, Titan or Europa or something, some moon around like Jupiter or Saturn. I don't know, whatever. Um, but if gravity was changed by some factor, then it would still be kind of a strange setup, but mathematically something relatively simple to do. Because the height would still be 1, it would be unchanged, the density would be unchanged, and then gravity would be in a ratio, new gravity to old gravity, of 0.5. So notice that all of these, if you have some reasonable value, end up giving the factor back again. Makes sense because it's a fairly boring equation. It's just find a bunch of stuff and multiply it together. Okay, then part of the reason that we learned about pressures, and in particular fluid pressures, is so that we can set up and see systems. So the hydraulic system changes the size of a piston from one side to another and can use that, excuse me, can use that to increase force considerably. Occasionally the pistons are the same size on either end, and basically it's just to transmit force through the means of fluid pressure, but we're going to look specifically where there's a small piston and a large piston. To help narrow this down and to make very clear what we're talking about, then for the smaller piston and the smaller force, I'm going to use lowercase letters. So F1 over R1 squared. Technically this would be related to the area here, but as you can see from our earlier example, technically pi was at both of those and could be canceled. If you really wanted to, you could bring pi back, but then it would stack in the fraction and cancel again. So it's up to you, but pi isn't necessary here. Okay, then thinking about how this is going to set up for the larger piston, we'd make some larger force due to some larger radius. So I'm going to use a capital there as well. Although I'm going to fix my horrible handwriting. I tried to fix it. It was bad. All right, but this is better. Okay, then if we read the question, we're going to find the new force from the larger end of the system. So that's the larger force. We're going to get this by itself. So you might be tempted to cross multiply and divide and fully work through the proportion, but don't do that. It's extra steps here. The only thing that really needs to move away is right here. So if we multiply by big radius squared, then that's going to cancel from this side. And then to balance, I'm going to do the same thing over here. And so that's really only moving one part away, but we get that the larger force is equal to the smaller force times the bigger radius squared over the smaller radius squared. And the fact that we have the big radius over the small radius here, I think, is also a clue that the force is going to end up growing from this. Okay, from here, we have a number of interesting variables to look at. I say that, and the first one's the boring one. But if we look at the force here, this one's not going to do a whole lot, but the other two are. So say we have our initial small force. Oh, there's that bug again. Have this initial small force. If we adjust that by some factor, then that's going to be 0.5. If the big radius isn't changed between different versions of this question, then the ratio there is going to be 1, and then squared because of the exponent in the question, and then similarly on the bottom, 1, and then squared. So technically what we have is 0.1 times 1 times 1, divide 1, because that's a bunch of 1s, though we just keep that factor, which for my made-up example was 0.5. Okay, and then now to the actually interesting variables. If we look at this radius from the top, so say that R2 is reworked in a new version of this question so that it's multiplied by a factor of 0.5. Look at where that is in the formula, kind of see how the variable is affected, and you might be able to tell where this is going to go, but let's check and see. So if that original small force is unchanged, then the ratio of the new version versus the old version of that number is going to be 1. Then for this larger radius, it's going to be 0.5. Don't forget that that gets squared because of here. That's related to the original area formula for the circle. Then in this question, the little radius is unchanged. So put it in the ratio itself will make 1, and we can plug in 1 squared. Those 1s aren't going to really do anything here. So we're getting it with 0.5 times 0.5. Basically, the factor is squared. And for my simple number, that just makes 0.25. Okay, and then last one to look at. So if we look at this one, say that the little radius is adjusted by some factor, then look at where that is in the formula. And again, you might kind of see where this is going. But the original little force is unaffected, so it has a ratio of 1. The big radius in this question is unchanged, so it also ends up being 1 when we plug in the ratio. Don't forget that it's squared, even though technically it's not doing anything here. It's a good habit to make sure that you're tracking that carefully. All right, and then here, 0.5 squared. So what we want to notice from this is that we end up with not quite just the reciprocal of the factor, but you need to remember that because of the area definition and the r squared that pulled across, that it's the reciprocal of the square of the factor. So for me, that's the reciprocal of 0.25. This one's actually going to become 4. So it makes a rather large difference on that one. Okay, then last one from that folder 3A material. Couple of little things to pay attention to. So our formula, we can probably reasonably skip to here. We know that typically if you're dealing with a nozzle or a hose or a pipe or something reasonably shaped, it's probably going to be a circle. So, you could have something that was a hexagon or triangle in a really horrendous question. I'm not going to do that to you. So what we're looking at then is the velocity is the flow rate divided by the area of the circle, so that's going to be pi r squared. Now, be careful here. You might be tempted to cancel pi because we did that on another question, but you have to remember why we did that before. There's no other pi to cancel with it at this point. Okay, then we have to keep in mind that the question gives us the diameter of the pipe. So that's going to be important to plug in here. We're going to have that the radius is equal to whatever the diameter was divided by 2. And then if we know what the radius is equal to, and we know where it goes inside of some other formula, then we can replace that information in here. Okay, so don't forget that that's going to get squared. And you're going to see sort of a variation on the area of a circle. This is something that engineers use often, especially for pipes, because pipes are round and typically classified by their diameter. So if you say you're talking about a 4-inch pipe, you mean a pipe with a 4-inch diameter. And so it becomes a lot more useful to use the new version of this formula that we're going to see. Okay, so this would say that the velocity is equal to the flow rate, which is q, and then the d over 2, think about that as 1/2 times d. That's going to get squared by this formula. And so we end up with 1/4 from the 1/2 getting squared. We still have the pi that's here, and then we have the diameter that's squared. So the major difference is because this has a divide by 2, technically you end up dividing by 4. Okay, and then if we look at how these variables are going to change, then flow rate is the most direct one. So if we had some flow rate and then we came and adjusted it, then, you know, this is one of our sort of boring ones. But the new Q versus the old Q has a ratio of 0.5. Then what's interesting here is that we'd have a ratio of 1/4 to 1/4 from pi to pi, and technically now we could cancel those things because they're constants. If you really wanted to, you could technically put in a 1 and a 1, but I'm not going to. Then what we're looking at, the diameter in this one is not changed, so we'd have a 1 here and then squared. I'm specifically keeping this one because it's talking about a variable and something we're going to look at later. But in our other example, the 1/4 and the pi are also going to cancel. So I feel like because they cancel all the time, we can ignore them at this point. Okay, but with that being said, if we finish working this one out, then we get, in my case, 0.5. And so that indicates that we got the vector back again. So whatever yours happens to be, you would see that again if you work through this similar question. Or if you decide to modify these numbers, work them out, you could divide your new answer by your old answer, and you should get something very close to whatever your factor was that you used to adjust the question. Okay, then the diameter is going to be the one that's a bit more interesting. Let's say that we have some diameter, and then it gets adjusted by some factor. Then think about how this is going to change and what's held constant, what was constant the whole time, and then how that's going to affect the answer. So in this case, the flow rate is unchanged. So the ratio of the new flow rate to the old flow rate is 1. Then the constants, technically we'd end up with 1/4 over 1/4, or technically 1 over 1/4 over 1 over 1/4. Anyway, that gets kind of tricky, but that's going to cancel. Technically the pi is in here and it would show up in the ratio and it would get canceled. And so all we're really looking for now is the ratio of the diameters. And then don't forget, because of part of the original area formula, that needs to be squared. All right, so this is going to be 1 divided by the square of the factor. So be very careful with that. So the square of my factor is going to be 0.25, and then it's going to be the reciprocal of that. So for my example, that's going to make 4. Okay, so now the start of the 3B material. So this is the one where we're talking about thermal expansion. So if something gets warmer, it tends to expand and get bigger. Keep in mind that you have negative expansion, so it means that something cools down, then it's going to contract, it's going to shrink. So if we think about this formula, the change in length is equal to alpha, where alpha is the expansion coefficient. Then that's going to multiply by the original length, and then it's going to multiply by the change in temperature. Now we do have to be especially careful with this part because the change in temperature, to preserve the sign and know what's positive and negative, know what's growing and what's shrinking, we need to take the final temperature, excuse me, the final temperature minus the initial temperature. So like we've seen before, we can make a substitution. If we know that this stuff is equal to the change in temperature, and we see another formula that has the change in temperature being called for, then we can cobble these together. Okay, so then that's going to tell me that my change in length is equal to my expansion coefficient multiplied by my original length, and then if I expand this, let's use parentheses, final temperature minus initial temperature. Okay, now similar to what we've seen in other questions where there was addition and subtraction, changing one of these only is not going to be a good clue as to what your answer is going to do. So we can't really do anything with that. If you have a question that says that one of the temperatures is changed, or that the initial temperature is changed, or the final temperature is changed, there's not an answer you can really get from that. What's going to happen is both of the answers, rather both of the temperatures would have to change together. So if you're told that the final temperature and the initial temperature are adjusted by some factor, then that's something that we can find an answer for. Because in that case, alpha would be unaffected, so it would have a ratio with itself and make 1. Then the original length, again, is unchanged. That would be 1. And then what would happen is the difference would be affected by that factor. Both of these would have that same factor, and then technically that could be brought out to the front, regrouped, and these could cancel, and we'd end up with just that number. So if that factor was 0.5, we would technically have 1 times 0.5. So that would give us a 0.5, or whatever factor you had back again. Okay, so that's going to be the one that you've got to pay a little more attention to, and the one that might give a slightly more interesting answer. Alpha is going to be kind of boring, because let's say that we had some alpha, and then we adjusted it by some factor. Let's say we cut it in half. Then if alpha is the only thing changes, then the ratio of the new alpha to the old alpha is just 0.5. Technically, alpha and alpha would cancel each other. The original length is unchanged, so it has a ratio of 1. Then if neither of these temperatures is changed, then that difference is changed by technically a ratio of 1, so it plugs in the same way. So this one also gives the factor back. Then I think you might be able to see what the length is going to do, but because I'm already working on these, I'll show it anyway. But let's say that we took that length and we changed it by some factor 0.5 times the length. Then alpha is unaffected, so we can plug in 1. The length is changed by factor 0.5, so we can plug in that factor. And if the temperatures are unchanged, then they're going to have the same difference, and that's not going to do anything. So notice that all of these have a couple of 1s in it, and then the factor multiplied together. The order is not important. Notice that they all end up giving the factor back. Notable exception, like I said, you have to watch out for. If one of the temperatures is changed, then this doesn't work. Notice that this is specifically for both of them being adjusted. Okay, then one of our questions dealing with gases. So we had questions 6 and 7 that used a variation of the combined gas law. This one has a variation of another formula that is still technically related to that combined gas law. But our formula says that our pressure in the first scenario divided by the density in the first scenario would make some constant number. We're not going to find that, but if we know that number is constant, then it would be equal to whatever scenario we had later. And so we'd have the pressure later divided by the density later, and we can make a proportion out of this. You have to be really, really careful because the pressures in these formulas absolutely need to be, well, absolute. So no pun intended there, but we need absolute pressure. So if we read carefully, we initial absolute pressure, so P1 absolute, that's fine. But we're given the final gauge pressure. And gauge pressure is typically a pressure difference between inside and outside of a system or between different parts of a system. That's an issue because that doesn't tell us the total amount that the atoms and molecules are knocking around and bumping into each other. So that's going to be a bit tricky, and that's going to be something that we don't like that we're going to have to fix. So this P2 absolute that we have to plug into this equation is going to end up coming from the gauge pressure here and then the atmospheric pressure added to it. So that's the slightly tricky part that's going to come from here. So this stuff is equal to that P2 absolute. And so then we're going to have to plug in for here. Okay, so bringing these things together, we get that P1 absolute over D1 is equal to P2 absolute, but remember we're substituting a bit here. So P2 gauge plus P atmospheric. Okay, and then divided by D2. All right, then we need to see what we're actually solving for. So this question calls for the final density. So that means I'm looking for D2. So this is the proportion. It's kind of ugly, but it is still just a proportion. So because of D being in kind of an inconvenient place, we really do kind of need to go through the whole process, cross multiply and divide. If you do that properly, then you're going to get that the new density D2 is equal to the old density D1 multiplied by this combination pressure that again adds up to make absolute. But that's that D2 gauge plus P atmospheric, and then that's going to be stacked over the P1 absolute that was given to us before. Okay, so kind of an ugly looking formula because there's some addition in there. This is a warning that I've given you several times. If there's addition in a question, you have to be able to change both of these things or all of the things being added before something can change. That's not going to work for this one. So if there's any change to this gauge pressure, because it's going to have something added to it, and then it's going to be multiplied and divided by some stuff, we can't predict where it's going to go. So to be very clear with that, if your P2 gauge pressure is adjusted by some factor, cut in half, doubled, however, because it's supposed to have something added to it, we just don't know what that's going to do. So another sad face on this one. Gauge pressures just really cause issues. That's part of the reason why we need absolute pressures in the questions. So we know the total amount that the atoms and molecules are moving around, exactly what they're doing and to what extent. Okay, then the remaining variables, I hope by now you're kind of getting a handle on these and seeing what they do, but let's confirm that. So if we look at this density, D1, it's in the top here. It's being multiplied by some stuff, but that's okay. Then the absolute pressure, again, you can kind of see where that's going. So let's work these through. If the original density is adjusted by some factor, then when we go to plug that in, the new density compared to the old density will have a ratio of 0.5 because of that factor. If the gauge pressure is unadjusted, then it's going to give back the same information, and so that would have a ratio of 1. This is a parenthesis. I'm going to fix my handwriting a little bit here. Okay. Then on the bottom, if that pressure is unaffected, then we could make a ratio of it with itself and we would get 1. And so ultimately, this is just going to give back that factor. Okay. Then one last thing to reasonably talk about if we're looking at this P1 absolute. So the initial or original absolute pressure, if that's adjusted by some factor, then you need to notice where this variable or where this information goes inside of the formula. And then you can kind of eyeball and see what's going to happen. But let's work that out for sure. So here, the original density is not changing. The final gauge pressure is not changing. And then what we're looking for, this is on the bottom. So the factor ends up here. Okay, so that's going to end up giving you 1 divided by the factor or the reciprocal of the factor. And because I use a nice number like 0.5, then that's going to turn into a nice clean number like 2. Okay, then there's 2 more we're going to look at out of this section, and then we're going to move into 3C. So this one, kinetic energy, we had an old formula for kinetic energy, which is actually going to cycle back around and show up in the next question. But this one, it looks tricky, but there's actually not a lot of information necessary. In fact, if you look at the original question here, there was only 1 number actually given to you. So let's think about this right quick. Kinetic energy is 3/2 of K. K is Boltzmann's constant, which is just its own special number. It's got scientific notation in it, but that's not going to hurt us here. And then multiplied by the temperature, which is required to be a Kelvin temperature. That's also called an absolute temperature. So temperatures and pressures must be absolute or else we can't make them work. Okay, but because these things are constants, and they are literal, permanent, real constants, there's nothing we can do with them. They can never change. And so all we're looking at here, let's say that your Kelvin temperature is cut in half. It's adjusted by some factor. Then the ratio of 3/2 to 3/2 is just going to cancel and go away. The ratio of Boltzmann's constant to Boltzmann's constant, again, numbers that aren't allowed to change, that's just going to cancel and go away. And all we have technically is just the factor plugged in. And for hopefully obvious reasons, that just gives back the factor. So this one's super simple. Worst case scenario, you could try this again. So, with my example of 0.5, you could look at this one from the previous notes or from other YouTube videos, cut that number in half, make it 111 Kelvin. Work through the answer, and it's going to be exactly half of this. So 2.2977, something like that, times 10 to the negative 21. And then if you stack those, made a ratio of that new answer divided by the old answer, you should get back 0.5, plus or minus some rounding error, depending on exactly how you plug things in and what you wrote down. But that's it for that one. Okay, and then where this sort of comes back around, I'm not going to show the full details for this, but our old definition for kinetic energy was 1/2 times mass times velocity squared. And then our new definition for kinetic energy, when we're dealing with gas molecules and how they move around, is 3/2 times Boltzmann's constant times Kelvin temperature. Now this one is asking us to solve for temperature, so we need this to be by itself. Kind of an interesting thing is going to happen here, though. So we can view this a couple of different ways. We can double everything and clear out the fractions, or we can sort of cancel the 1/2 from both sides. Let me do that in a new color to make that easier to see. But we can cancel basically the halves part of these, and then that 1 doesn't really matter anymore, and this is just 3. And if I want to get this temperature by itself, then technically I'm dividing by 3 times Boltzmann's constant, which according to my handy dandy note reference looks like 4.14 times 10 to the negative 21. That's really small and hard to read. But you can, maybe that's 23. I don't know. It's too small. I can't read that. But you can check back in the old notes and see. It's not going to really matter because remember these are constants, so they're not going to really factor into our ratios and the parts that we're talking about. But anyway, if we finish rearranging this formula, you end up with the mass, and we need to be careful and remember that this is the mass in kilograms, but that's an adjustment that we would have made during the work, times velocity squared divided by 3 times Boltzmann's constant. Okay, like the previous question, which was number 8 from the old notes, 3 and Boltzmann's constants are just constants. 3 is a number that can't change. It's just part of how this got built. And then Boltzmann's constant can't change without, modifying the way the universe works. So the mass is the only thing that we can reasonably pay attention to. And if that mass is adjusted by some factor, then, well, that's that's pretty much what this is going to make, right? So the ratio there is 0.5. If the velocity is the same, technically it has a ratio of 1, plugs in and gets squared. Then the 3 and the k from the bottom, these are just magic numbers. They get canceled. And so this one's going to give us back the factor. Then if you're looking at this carefully, excuse me, I think you're going to see that the velocity is not going to be quite so simple, but it shouldn't hopefully be too tough. But your velocity, if you multiply that by some factor, you have to think about where it is in the formula and sort of the major features around it. I should have made my 0.5 taller. These are meant to be lowercase v's. Apparently I made lowercase 0 and 5 as well. Whatever. All right, but the mass is unchanged, so it has a factor, or rather a ratio of 1 with itself. And then the velocity is a ratio of 0.5 because of the factor that I've made up on all of these. And then you have to remember that that gets squared as part of the formula. Okay, so it's the factor squared, which for me makes 0.25. Okay, and then like I said, it doesn't make sense at all to say that 3 and Boltzmann's constant will change because those are both just numbers that should be the same all the time. Okay, then that takes us into 3C. Now, this one is a simple enough question, Now, technically, the nice thing is that the way that we view this is going to cancel out the difference. But the thing is, we're trying to find calories from this, and we're given a number of joules. So basically, that's just a conversion. Um, what's going to happen is that conversion number, depending on where you look it up, can change a little bit. So sometimes the joules and calories conversion, you can look it up, and it can be 4.184, 4.186, 4.19, 4.18, 4.2. There's a lot of slightly rounded numbers, technically because it's dependent on temperature and pressure. Now, here's the nice thing. So we can build out our formula based off of that conversion number. And so my energy in calories is going to come from my energy in joules divided by whatever conversion number the textbook says. I believe ours uses 4.186. Well, that's a conversion number. It's not subject to change without changing a whole lot of other stuff that we don't have answers for right now. So the only thing that really can be adjusted is just the number of joules. And so if we have a different number of joules, say it's adjusted by a factor of 0.5, because that's what I've been doing. Um, that's really the only number we're looking at, right? This would end up divided by the same number if we were to force through and show the work. And so I think it should make sense, hopefully, that all we're really looking at is just 0.5 or whatever factor you're using. And we get that number back again. Okay. Then this particular week of content, there are a couple of beefy, ugly looking questions. So a few of these that we have remaining are not super nice to look at. So technically, the formula that we see in this one is the longest single formula that we have in the whole semester. And it happens that way because technically, one formula gets duplicated and set equal to itself, and then slightly expanded to fix the direction and the signs. So this is also on your formula sheet, giant mega formula. But we have that the mass of a metal in the scenario multiplied by the specific heat of the metal in the scenario times the change in temperature of the metal in the scenario. Well, to save a little bit of space, I'm going to go ahead and put that here the change in temperature, because we want this to stay positive with the way the formula is set up, is going to be whatever high temperature we have for the metal minus whatever final temperature it gets down to. Okay? And then that's how we would find the heat that is lost by the metal. Then that exchange of heat and that conservation of energy says that the water sample is going to absorb that and it's going to raise temperature. So we'd want to find similar information about the water. So mass of the water times the specific heat of the water times the change in temperature of the water. Now, the order here is intentionally flipped to preserve the sign. The formula has already been very slightly rearranged even before what we see here to make sure that the signs are going to work out the way we want. And so here we'd have the final temperature, because the water went up, that's the bigger number, minus the original low temperature. Okay, so then now we want to find the specific heat of the metal. So we're looking for this thing, which means we need to divide all that other stuff away. So I'm going to bring this, I guess I can make it go this way. But we need to take these things, we need to divide them and bring them under. And so I'm going to end up that the specific heat of the metal is equal to the mass of the water. Oops. Make that a subscript like it's supposed to be. Mass of the water times the specific heat of the water times the change in temperature of the water. But again, because that went up, we specifically subtracted final temperature minus low temperature. Okay, and then that gets divided by the stuff from here that needs to be brought over. The mass of the metal times the change in heat of the metal, which to preserve the sign needs to be the high temperature minus the final temperature. Okay, so that I know that could be kind of scary looking. The specific heat of the water we're going to take to be as a constant, so this thing's not going to change. You can see it as slightly different units. So sometimes the number won't be exactly the same. Sometimes you'll see it as 1. if it's in calories per gram degree Celsius, or occasionally you'll see it as 4.186 or 4.184 if it's in joules instead of calories. But that's just some constant for water. The rest of this would all be things that can change. So let's deal with the simple ones first. If the mass of the water is changed because it's in sort of a boring spot in this formula, if the mass of the water is adjusted by some factor, then we would end up with 0.5. I'm going to go ahead and say the specific heat of water is a constant, so I'm not going to look at that. If the temperatures are unchanged, then that difference is going to have a ratio with itself of 1. If the mass of the metal is unchanged, and again there would be a 1. If these temperatures are still unchanged, then once more a 1. Okay, then that's going to give the factor back. Okay, then I'm going to leave off talking about the temperatures for a minute. So we already said that this is constant, so that's not going to change in your questions. But let's say the mass of the metal is changed. So we can bring that down here. So mass of the metal is adjusted and changed so that it was half of what it used to be. So new version of this question, again, you could take the 117 divided by 2, work the question out, and see how the answer changes. But what that's going to do for you, you're going to have the same mass of the water. Like I said, I'm ignoring this constant because I assume it's not going to change. If the temperatures are the same, then they're going to have the same ratio. Then the mass of the metal is the part that we're looking at. So this is going to be in 0.5 because it's going to change by that factor. And then if the temperatures are unchanged, then that's going to be ratio of 1. So pay attention because what we're going to have here is the reciprocal to that factor. And because I picked a nice number, that's going to give me a nice answer, and that's going to be 2. Okay, then if we have individual temperatures changed, then that's not going to do anything that we can reasonably predict. If only the final temperature is changed, it's very difficult to see how that's going to make a different change here and a different change here and come up with some answer. If only the low temperature changed, then again, that's going to be very difficult to see how it's going to affect everything else. So the only way that you can get a reasonable answer out of different temperatures is if they are all adjusted by the same factor. So we would have to have the low temperature, the final temperature, and the high temperature. All of the temperatures would have to be adjusted by the same factor. Okay, and then that's probably still not even going to do what you expect it to do. So let's see what that makes then. So again, if we adjust this by some factor, it has to be all of them: low temperature, final temperature, high temperature. That means the mass of the water is unaffected, so ratio of 1 compared to what it used to be. Specific heat of water, again, we're going to say is constant, never changes, so we're not going to include that here. In this case, that means that this difference, if everything's adjusted by a half, this difference is going to be changed by a factor of a half. Because technically both of these things will be multiplied by 0.5, and we can bring that out of the parentheses, sort of the opposite of the distributive property. And then, now that might be a hint for what's going to happen later, but for right now, the mass of the metal is unchanged. These would both have a 0.5, and so technically we'd draw them out as factoring, and we'd have a ratio of 0.5 that's going to show up here. So what you end up with is 0.5 over 0.5, or the factor divided by itself, and that means that the answer to this part is 1. And so that means that if the temperatures are all adjusted by the same factor, if they're all doubled or tripled or divided by 4 or whatever, then the answer in the end does not change. And that's really strange to me, but that's how it works out mathematically. If you change one of the temperatures, it's gibberish. If you change them all by the same factor, it ends up not doing anything. So it was something I always thought was weird. Oops. Okay. Then we've got 2 more to look at from this section. This one gives us kind of a small break, and also, if you're paying attention, kind of a quick sneak peek at what we're going to end up with. But very quickly, if we're changing the the phase of a sample, and that's all we do. There is no temperature change. Until a whole sample of ice is melted, it's going to stay at the same temperature, the freezing or melting temperature, depending on which way you're going. We call it by slightly different names. So 32 Fahrenheit or 0 Celsius will be the temperature of the ice until all of it has melted. And then at that point, you can warm up the leftover water if you want to, which again, like I said, is potential for shadowing. But for right now, Q, the amount of heat or quantity of heat necessary is equal to the mass of the sample multiplied by something called the latent heat of fusion. That's some constant or some magic number that you can look up from your textbook. And so because that's a constant, the only information I actually need here is just the mass. And so if the mass is adjusted by some factor, so say it's cut in half, because that's what I keep doing with these, then all I have is just the factor of 0.5 plugged in. This is a constant. This is not allowed to change. So I'm not even going to bring it down and show it in my work. I'm just going to say that it ends up being the factor. That doesn't mean that this question can't trick you if you're not paying attention, because if the question mentions, starting temperature, final temperature, change in temperature, any of those things, there is no change in temperature. So you either change the material by changing phase or you change the temperature, but you're not going to be doing both at the same time. So, those are the ones that are going to not make sense. If it says anything at all about temperature, doesn't even matter how it says it changes. If it mentions temperature, then that is something that you can't do. It will not make sense. So just pay careful attention to that. Now, ironically, that's kind of the exact opposite we're going to see in the next bunch. So this question has a lot going on. It's closest, matched most closely to question 10, the final question of the week. But even then, that one was slightly modified to save time in previous semesters and only really encompasses questions 5, 6, and 7. So this one doesn't really have a direct match other than it's like all of these put together in one giant question. And so you've got all these different formulas, you've got all these different constants. Actually, a lot of this is just not going to change. And so what I want you to see from this is that the only real consistent thing between all of these questions is the mass. See, this has a change in temperature and that one doesn't. This has a change in temperature and that one doesn't. This has a change in temperature. So it alternates between the two major types of formulas. There's one they call the MCAT formula, because if you kind of squint a little, the delta of the triangle kind of looks like a capital A. And as a memory trick, like the medical school test is called MCAT. And then this is the ML formula. And there's latent heat of fusion and latent heat of vaporization, but both of those are just magic numbers for how phase changes occur under sort of standard temperature and pressure rules. Excuse me, I should say not standard temperature, but standard pressure rules. Okay, then 3 of these do have C's, but if you pay careful attention or if you thought about the notes before, the C is a specific heat constant or specific heat capacity of different substances. So solid water as ice and liquid water as, well, just normal water, and gaseous water as steam all actually warm up differently. This one is 0.5, this one's a 1, this one's a 0.482. So all of those are even different from each other. You can take all of these formulas and you can sort of refactor and do something new. Excuse me, I get to the last one and I'm slightly losing my voice. But anyway, to be consistent with this, to look at all these formulas and regroup, I don't have a lot of space here. So I'm just going to go ahead and refactor these numbers. It's going to include using the constants that are in here, and then the fact that the difference between boiling and freezing temperature is always the same 100. If we bring all of these things together and take all of these Q's, so if this is Q1 and Q2 and Q3 and Q4, and we understand that these are all going to have to be added together to get the total amount of heat necessary, and do a whole bunch of algebra stuff, we get this magic formula. So I'm going to put stars around it because I'm going to call it the magic formula. And that Q, the total quantity feet for all of these things put together, is going to be the mass, which again is the only thing consistent from all of these, multiplied by 0.482 times the high temperature, so whatever the steam gets up to, um, minus 0.5 times the low temperature, plus 670.6. Okay, so a lot of crazy stuff is happening with this. We have the difference in temperature between 0 and here. We have a difference in temperature from 100 to our steam. We've got temperature between 0 and 100, and all these things get refactored and turn into this. There's a lot of addition and subtraction, and as you can see, because there's a whole bunch of formulas we put together. And so this is the one rare case that even if I say all the temperatures are changed by a certain number, well, it's not really all the temperatures. We can't change when water boils and freezes. And so if you say anything about temperature, any variation on temperature, temperature is going to lead to sadness. Can't do anything with that. So the only predictable thing that we can look at and guess and see how the answer is going to change is just from the mass. Okay, and so let's say that the mass is adjusted by some vector, 0.5 times the old mass, and so there we go. Then these are going to be in a ratio of 0.5 for whatever that factor was. And then it's going to end up multiplying by all that same garbage. None of that can change if we're going to get an easy answer. And so it would end up just being the factor. So as long as the original temperature and the maximum temperature are the same, then we get the same stuff back again. So I guess we saved the most interesting and most potentially scary looking one for last. But that's everything we need to look at. So that's it.